Okay, let's begin our second lecture. Uh, what we are uploading instead of taking live classes. Okay, we can go back to discussion. Well, the resource blocks that you have for a particular type of spacing, if you have multiple, then you have different set of uh, resource blocks for each of the separate spaces. And these are called common resource blocks. So if you have 15, 30, and say 120, so you have three sets of resource blocks. So each are three sets of common resource blocks numbered this way. Now the bandwidth parts are again something to allow additional flexibility. Now in 5G, the bandwidth can be very large. The be maybe operating uh, using a very large bandwidth or the total bandwidth of operation recognized in the system is very large. But the EV may be capable of supporting a small range of that whole thing. So there is a provision for bandwidth parts, but you can see that this is a good example. Uh, Probably you remember that there's something called carrier aggregation. We discussed for LTE that the maximum bandwidth can be 20 megahertz, but this type of 20 megahertz bandwidth chunk, you can have more than one. So it doesn't have to be 20 megahertz. Even if you have 5 megahertz, there can be another 5 megahertz operation at a frequency which can be, anywhere, theoretical. So with these two carriers, you can use together for a particular E, and is that called carrier aggregation. And this way, 5 carriers can be added at the maximum in the case of LT. So, if I uh, consider maximum bandwidth for each of them, then the total becomes 100 megahertz. That's the maximum bandwidth support for LTE. But in the case of 5G, it can be very wide, and but your EV may support a part. May have some limitation. So there, you can actually have all different types of configurations. It's up to you how you do. Like for example, if I have two carriers at some two frequencies, okay, uh, they are located at two operating bands, and you have bandwidth part. You just have single bandwidth part for on each of them. So from megahertz, so it is possible that you have a carrier aggregation between them. Now, if you have, but we can also define that I have two different bandwidth parts. This carrier support, okay, the E node is supporting 500 megahertz, but you considered it to be split into two parts, uh, and the E is configured to work on any of them. So in that case, you have bandwidth part, but the EV at a time will not be able to use more than one bandwidth per carrier. Only single, you see here it is written, only a single bandwidth per carrier can be active at a time. but multiple on different carriers, uh, different bandwidth parts can be active, and there can be a carrier activation. Okay. Now the UV can be configured at most uh, 4 bandwidth parts for a carrier. The maximum limit is to have 4 bandwidth parts per carrier in either downlink or uplink, as shown here. But you know that at a time only one of them can be active. So here you see, I mean, the, so many different bandwidth parts have been created, and the E is configured this way. Right? All these bandwidth parts are available for the EV. But at a time, say we could have BWP1 from here, and say BWP3 from here, then BWP0 from here, BWP1 from here. You may aggregate. Channel bandwidths, these are the allowable channel bandwidths. Okay. For FR1, we have, and for FR2, can be very large. For synchronization, we have 20 resource blocks. Let me show you the uh, uh, like LTE, there is also PSS and ASSS. When it uses correlation to determine, and their locations are, we are not going into the detail, but we're showing the locations. So when the captures first, it like before, it keeps trying correlating on a symbol, and then it tries with the next symbol. It keeps on doing that, and when it finds also along the frequency, okay, it tries to capture the right location. Let's say PSS is located this way. Once it can capture PSS, uh, exactly like before, you have 3 different options possible for PSS. It will be one of 3. The first capture has to be very simple. The available options have to be very few. Like here, you have only 3. So you try with just these 3. So one of them should hit. And once you find out PSS from its location, you also find out the location for SSS. And also, I'm sorry, you find out the location for PBCH, which carries the mid. So the blue part here is carrying mid message. That's it. There's nothing else there. Now this SSS has more options. In the case of LT, you had 168. Okay, so the total number of possible PCI was 504. But here it is a little larger. It's because you have to go to that. It's because in the case of 5G, you have very small cells. Uh, you have the provision for a very small cells, and this creates the radio planning even tougher. You have okay. Anyway, there are, I mean, SSS instead of 168 can have 336. Oh yeah, 336 groups. Okay, the possible um, variant for SSS is 336. So the total number of PCI is possible 3 times 336. Uh, that is 1008. So you have more. It's actually twice as much as the number of PCI for LTE. Okay. So even if you have very small cells and in the downtown area, and the radio planning is very tricky, but the available PCI is so many that hopefully there won't be any repetition of the PCI in the neighborhood. So that is just increased. Then the location, I mean, this block, it is called SS by PBCH block. This whole thing, this whole thing is called, sorry, this whole thing is called synchronous signal PBCH block. So this synchronization identifies the location of this block in the time frequency grid. Okay, and also identifies PCI. Right? Now, for downlink channels, as you can see, you have the same channel mapping as we had for LT, with small differences like say DMRS. Actually, DMRS we also had in the case of LT. Okay, I mean there's not a difference here, but the use of DMRS is more in the case of LT, and in LT, even in 5G, it is more. In LT, the term DMRS is used in the case of uplink. Okay. So it, the same concept was there also in downlink, but the terms were different. Now, what the purpose is? The DMRS is a set of known symbols, and that helps estimate the propagation channel. So you can adjust the receiver circuit to the equalizer and all that to match the propagation channel. So when you decode the known symbols, so it is inserted within the within your transmission. So when you are sending your PDSH, some of the symbols in the time frequency grid, all the symbols you don't use for your PDSH data. Some of the fixed, there is a set of fixed locations within the time frequency for PDS within your PDSH part, which are set for DMRS. Okay? They will carry known symbols. So when the receiver decodes the known symbols, maybe the decoding gives little different results, okay, different from expectation. So it adjusts the equalizer and everything, okay, on the receiving part until the reception of DMRS is perfect. And the same adjustment is used for the whole PDSH. So that way, PDCCH or PPCH, they all have this DMRS type of symbols inserted. CSR is channel state information. I mean, CQI is the most important part of CSI. Also, it carries feedback from memory. Okay. The other channels have the state that. Okay, a lot of things are very similar, so I don't need any. Uh, I mean, I can quickly skip like the paging procedure, random access procedure are actually the same as you have for LT. Uh, I'll just mention where you have small difference, where you have differences from LTE. Okay. And you see, I mean, this whole part is it's 20 20 resource blocks wide, as you can see here. So the actual length depends on your subcarrier spacing. It's 20, the SSPP by PPCH block, 20 resource blocks wide. And at the center, I mean, this one is marked subcarrier 0, which is the, I mean, the center is marked at subcarrier 0 of resource blocks 10. So this is what at the center. And that really resource blocks range will definitely differ uh, according to your subcarrier spacing. Yeah. I selected some pages from the book, and this PDF is uploaded. It is uploaded. You see that you have different ranking. The same type of almost all these ranking you also had for LT. The term TC may look different, but actually you had it for LT. You will remember that we mentioned at one stage of random access procedure that the E node B assigns a C and that C can later be made permanent or a new C can be allocated. So that C didn't have any special term before, but now it is called uh, temporary C systems for cell radio network temporary identifier. So it's temporary serenity. Okay, so you had it before for NT. Now MCS serenity, CS serenity, this looks different, but this CS serenity is like what you had for SPS rate, same semi-persistent schedule. Semi-persistent is done a little differently, but I mean you have uh, a different rate when you use semi-persistent. Now the serenity also is different, or it takes on a special value when you use very low frequency MCS. So that's an addition. We didn't have this option for LTE. You see, in the case of 5G, the IoT applications, both IoT applications and uh, the high reliability, the extreme two cases of the bottom part. And this one completely deals with IoT. You have many different devices with very small data rate. You have to just support a high number of devices. And here you have some requirements in terms of latency. But these are also basically some end-to-end applications. So these are, and they are nothing but again some sort of IoT. Uh, so these two, I mean, we had this at the left and right corner at the bottom. Now, in these cases, the data rate requirement is typically low. Okay? The data rate increases upwards. this set of applications. So with the low data rate, especially, I mean, if I go towards right here, the reliability, yeah, basically you say this URLC application, you got high reliability but low data rate. In that case, you need low code rate. Okay? Your spectral efficiency doesn't have to be very good. You can sacrifice that uh, for the sake of lower code rate. Now, for MCS setting, we discussed a table. Uh, we talked about 27 levels, each indicating a particular modulation level and code rate level. So the same type of table we have here for 5G. In fact, in total, we have 32 rows from 0 to 31. We have 5 bits long MCS field, which you can use for the setting purpose. Now, this table has multiple forms, especially mainly because you have different level of maximum modulation support. Let me go there. Yes, I'll jump to that page. Yeah. Yeah. Let's go sequence for sequence 15 percentage. Table that looks similar. Yeah. So the maximum modulation support is 64, in the RD NT specifications. And it's increased to 256 and then 1024. If you go to the state, I think the basic number is 36 to 11, or it can be 36 to 12. For LT, I mean, here it is 38 to 11 or 38 to 12. So there you'll see on this 32 levels, the modulation levels and the code rates. Okay. In the uh, I mean, that can it is shown little differently, okay, relating to the transport block size. But anyway, basically you have the code rate, the modulation level. It just indicates when data is allocated either in downlink or uplink. MCS field indicates this index. Okay, so we know what has been used. But you need in the specification book, you need separate tables. If the maximum support is 256 QAM, then you actually use this table. Then your index 17 will indicate this one, okay, which is little different from here. If your index 24 will indicate this modulation port rate, whereas in this table it is different. Okay, so the maximum modulation support in the system actually dictates, or you need actually separate modulation, I mean MCS table. Okay. So that is why at present, I mean, if you look at the present specification book, you'll find another MCS table which ends with 1024 QAM. Okay. Now, apart from them, okay, there's a there is another table. So now you'll find one, two, third for 2024 QAM, and then a fourth one, which is used with lower code rate. You see, for any level, say, I mean, we compare with this guy. Say here, 15. Okay? This 15 uses 16 QAM, but code rate is 6.2. But you see here, 15 uses 16 QAM, but code rate 0.332. Also, the modulation level is little lower. I mean, at 40, it is still TPS gain. So with the little lower code rate, or sometimes even the modulation level, we can achieve better reliability. It will be less likely to have some basic error. Of course, the spectral efficiency will be lower, but this lower spectral efficiency is fine for you because the IoT applications, okay, these or those URLC applications, require very low data rate typically. So spectral efficiency uh, can be low for your application. But I mean, to handle this special case, we again need a separate uh, statement that is given here. Well, once you have this access tables this way, the SQL tables will also be uh, available with these different options. Okay, so now you have, I mean, you have one more right in between, another SQL table with 1024 QAM as the maximum issue. So SQL will indicate with one of its 16, 15 index what might be the best uh, you know, might be the best access level for downlink data transfer. Okay. But you see, for spectral efficiency, you have a spatial level for SQL. Okay, let me wrap up now. I'll create another session for the rest of my discussion. Thank you.